Okay, this is just a file to redo the notes for 10.3 that had gotten messed up. So I'm going through the notes real fast again. I'm not, since I don't have any questions or anything going, again, I'm just going through the notes real fast in case anybody had missed this set of notes and wanted to watch a video on it instead of just copying from the notes. So for 10.3, we're talking specifically about chords. Now, when we have chords, the essential question for this is, how are chords related to their central angles and the intercepted arcs? Now, first off, a chord is any segment whose endpoints are on a circle. So there's lots of different types of chords. And we've talked about one chord in particular in an earlier topic, which was our diameter. And I had talked about the diameter as a chord that is the longest chord in a circle, and it's also a chord that has to pass through the center of the circle. So again, but a chord itself does not have to be a diameter. It can be any segment whose endpoints are on the circle. So in the example here, all of these lines segments are chords. So RS is a chord, TU is a chord, SCU is a chord, and TR is a chord. Now, let me go back to this for a second. So on this question here, if you have two intersecting chords as SU and RTR, they're going to intersect and create vertical angles. Well, if those are vertical angles, then we know vertical angles are congruent. So on here, draw. Okay. So on this diagram, since these are vertical angles, these angles are congruent. And if those angles are congruent, that would mean that these arcs would have to be congruent, because if the angles are congruent, we know that the central angles, when they intersect an arc, have the same measure. So this arc and this arc then would have to be congruent. And then we can also say that this chord and this chord would have to be congruent, because chords that intersect the same arcs are also congruent. So since this is an intercepted arc with this chord, and this is an intercepted arc with this chord, and those arcs are the same, the chords have to be the same. Now, there are a lot of theories in this section, so I'm going to try to go through them as quickly as possible, but make sure I don't miss any of them. So now, on this one, try it. Why is angle BAC congruent to angle DAE? So we have the two angles in the middle. They're asking, well, these two angles would have to be congruent, because if the chord here and this chord here are congruent, that would then mean that these arcs must be congruent. So arc CB and arc DE would have to be congruent. And if those arcs are congruent, then the angles would have to be congruent. So this is the exact opposite of what we just stated in the last example. So why are they congruent? Well, we could say, if we wanted to do this in the if-then format, if what they gave us to start off with was segment BC was congruent to segment DE, then we can say the arcs are congruent. So CB as an arc is congruent to arc DE. And if arc BC is congruent to arc DE, then the central angles that intercept those arcs are congruent. So then angle BAC is congruent to angle DAE. So that's why they're congruent. Let's go to the next slide there. So lots of theorems. Like I said, there's lots of theorems in this section, and it's all about what parts are congruent when you have different chords in a circle. So in this theorem up top, this one's basically going over a lot of the same ideas that we just mentioned. So if two chords in a circle, or in congruent circles are congruent, then their central angles are congruent. So not only could you have two chords in the same circle congruent, but let's say I had a second circle over here that was the same exact size. Well, if we have two circles that are the same exact side, and we had another chord, let's say a chord drawn right here, and we said that this chord was congruent to this chord in that circle, well then this arc would also end up being congruent to that arc, and the central angle, if we drew an angle to a center point, this angle would end up being congruent to that angle. So again, it doesn't have to necessarily be in just one circle. So the next theorem there for theorem 10-4, if two arcs in a circle or incongruent circles are congruent, then their chords are congruent. So again, this is one of the ideas that I already hit on. If the arcs are congruent, then the chords are congruent. If the chords are congruent, then the arcs are congruent. Notice there's a converse for each one of these. For every single one of these theorems that's listed here, the converse is also true. For the next one, if chords are equidistant from the center of a circle or the centers of congruent circles, then they are congruent. So that's saying that if, in fact, this piece and this piece, so FS and SE are congruent, then the chords DC and AB are congruent. Now, the same is also true going the other way. If these two are congruent, then the length or the distance from the center is going to be congruent. Something else that's important to note there, you have that right angle, because if you're talking about the distance from that center to the chord, the distance there is going to form a right angle because you're talking about the shortest distance to it. And there's another important property there, that is always going to be not only perpendicular, but also bisecting that piece. And that leads us to the last theorem here, or second to last theorem. So if you are looking at the distance to the chord, or again, you could do this with a radius, or you could do it with a diameter. But if you drew a perpendicular distance to that chord or through that chord, whether it be just the distance to the chord, a radius, or a diameter, doesn't matter, it will be bisecting it as long as it's going through the chord at a perpendicular, or it's perpendicular with that chord. So if there's a right angle there, that means that it must be bisecting it. So then the final thing there, the final theorem, the perpendicular bisector of a chord contains the center of the circle. So if you were to draw the entire perpendicular bisector, it would have to go through the center of the circle. So all these are related, but again, there's a lot of different little theorems here. So lots of different ways that you can do problems with these. This is just a summary as to the two main ideas from this section on how the chords and arcs are related to one another. So let's take a look at a couple of the examples. Explain why all diameters of circles are also chords of a circle. Well, if it's a diameter, it has two endpoints on a circle, therefore it must be a chord. Because again, if we draw a circle and we draw a center point and we draw a line segment through it and we have 2 points on the circle, the only thing that's required for it to be a chord is the fact that the endpoints are on the circle. So a segment with endpoints on a circle. So we could say, why are diameters also chords? Because a diameter must have endpoints on a circle. Now, for number 4, given RS and UT are congruent to each other, and again, it's talking about the arcs, arc RS and arc UT are congruent, how can you find the measure of UT? Well, if those arcs are congruent, that means that these chords are congruent. It also is telling us, well, this side here, we have this piece is going to be equidistant. So we can say that those are equidistant. Oh, let me do 3 lines there. We also have this radius drawn in, so we can draw a radius in over here. It doesn't really matter which way you draw the radius, but we need 2 sides basically. So if this radius was 5.5 for QS, QU is also 5.5. We already have this side, and we now have this nice little right triangle that I'm highlighting in red here. And since we have a right triangle, we can find the third side of the right triangle using Pythagorean theorem. So c squared equals a squared plus b squared. Now, when we plug into this, we're going to be able to find the length of this little piece here. I'm going to go ahead and call that X for right now. We have the 5.5 is going to be our C value. So 5.5 squared equals 4 squared plus B squared. So now we're going to multiply this out. We have 4 squared is 16. Whoops, don't need the squared anymore. Get rid of that. Scratch it off. B squared on this side, 5.5 times 5.5 is going to give us, I think it's 62.5 maybe, but I'm going to type it in real fast just to make sure. No, I was way off. All right, 5.5 is 30.25. I did double that somehow. So 30.25. So we take that number, we subtract off the 16, so minus 16. We get 14.25 equals B squared. We take the square root of that. Can't find square root key on this calculator. There it is. It's going to be 3.77. And again, that's an approximate value for B. Now, why is that important? Well, that gave us half of UT. We need the whole thing, so we need to double that. So take that number, times it by 2. So times 2 is going to give us a total of 7. I went off the screen. Oh, no, I made random marks up there. 7.54. Oh, and if we round it up, really it should be 7.55 if we round it up. So 7.55 would be our answer. All right, moving on. For the next one, how do you know? So on this one, we are looking for a couple of missing pieces here. They want us to identify some arcs and some lengths of different pieces. So I'm going to actually go ahead and do the arcs first because I think the arcs are the easier part of this problem. They have AB. Now, if you look at this entire problem, a lot of things on here can be marked as congruent. For example, these can be marked as congruent. And the reason why we can say that those two are congruent is because it told us that AC and DF are congruent, are equal in measure. So if those two are equal in measure, in other terms, they're congruent. So if those are congruent, then the distance from those to the center has to be congruent. Now, if that's the case, each one of these little pieces is congruent as well, because these are being bisected. Not only is that being bisected, but the arc itself is being bisected. So we could even say things like this piece is congruent to this piece, which are also congruent to these. And then we can also say that these pieces up here are congruent to these arcs down here. So lots of congruency going on here. So we can fill in all sorts of stuff. If we know that arc AB is 43, that means that that arc's 43, that arc's 43, this arc's 43, this arc's 43. And if we do the arcs together for this entire length here, we even know that this is 86. So there's a lot of different things that we can fill in here about those pieces. So let's look at some of the arcs, because I think we already solved most of these over here, and I was just writing things that were congruent and adding things up. Measure of arc AC. AC, that's the entire span here, that's 86. So this is going to be 86 degrees. DE, that's this little piece, that's going to be 43 degrees. And DF, it's the entire thing again, so that's 86 degrees. Now we want the length of DF. Well, if we know that this piece is 2, we also know that this piece is 2, and this piece is 2, and this piece is 2. So we can go ahead and say that DF, the whole length, is 4, because we're adding those two pieces together, and we're getting 4. FH, that's half of it, it's going to be 2. AC, that's the whole length again, on the other line. But again, 2 plus 2 is 4. And that's it. So moving right along, the homework for this section was these practice problems over here. Again, it was everything from number 18 all the way through 27. I did not want you guys doing the proof, so it's just those. And again, hopefully this video helped if some of you guys were having difficult times with some of these.